Okay, so the reading for today was categories with products and Homsets. So at the end of chapter 2, and then next time we'll do the exercises. All right, so I'm just going to share my notes as usual. And here they are. Kind of big. All right. Okay, so this section is about categories with products. And Awodi tells us what that means. So a category is said to have products or to have binary products. If we have two objects A and B, and there's an object which is the product of those two objects. So the category has products if this works for any two objects A and B. That is, all pairs of objects have products. And if we have binary products, then we also have ternary products. That is, we can always take the product of an object together with the product of two other objects. All right, so the product of A and the product of B and C is also isomorphically the product of A and B, together with C. Right, so if we have binary products, then we can compose binary products for any finite number of factors. And he goes on to say that this works not just for like 2 and 3 and up, but also for 1 and 0. So we have unary products. We can see any given object as the unary product of itself. And the projection from the unary product to the member of the product is just the identity function. And the universal mapping property there just says that, for any arrow from X into A, where A is the object in consideration, there's a unique arrow from X into the product, the unary product of A, such that, the projection composed with that arrow is F. So since the projection is just the identity function, this whole construction is really, really trivial. So we can say that we have unary products. And the nullary product is a terminal object. So the way that works is that it's a product of no objects at all, right? And if we think about what the universal mapping property of that should be, is that, given no arrows at all, and some object X at the top of the sort of project diagram, there's going to be a unique arrow from that object into the nullary product, 1. And that's the definition of a terminal object. So for any given other object X, there's a unique arrow into the terminal object. All right, so nullary product and terminal object are the same thing. And you can also see that this works such that so that the product of the nullary product together with some other thing. So the nullary product is an identity for the binary product, right? In a certain sense. So like unit and A is the same as just A, right? Okay. Then he goes on to talk about sort of non-finite products or index products. So since we can think of unary products and binary products and et cetera, then we can think of the product object as being indexed by some number. But we can also be just indexed by any arbitrary set I. So then the product will have one object, Ci, for each element I in the set I. So if you think of think of a category that has some objects, and some of those objects we're going to call Ci, and there's going to be one such object for each element in the set, capital I. So imagine, for instance, that I is the set of natural numbers. Then for every natural number n, there's going to be an object Cn. So there's going to be an infinite number of objects like that. And what we're considering is the product of all such Cn. Right, so it's a sort of an infinitary product. What the universal mapping property says here, so that's left as an exercise by Wody, but we're just going to do it. The product P of all such indexed objects Ci is going to be some object P, right? For which every for every I, it has a projection pi, so pi I, which goes from the product P to the component of the product at I, right? And that's so such that for any other object X and an arrow F from X into that same component, there's going to be a unique arrow from X into the product, such that that projection composed with that arrow is the arrow F that we were from X into that that object Ci, right? So as a universal construction, as we went through that a couple of sessions ago, how to get to products from universal constructions. So this is really similar to binary products, except with a binary product, we start with a set 2, right? So the binary product is like an index product indexed by the Boolean set. So it's just a set with 2 objects in it. But we can consider any such set. And as a universal construction, let's say that we start with I, the set I, and we regard that as a discrete category. That is, it's a category that has no arrows except the identities, and the objects are the elements of I, right? Then there's going to be a functor from that category into C, which is the category we're interested in taking products in. And each such functor is going to pick I objects from C. That is, for every element in I, there's going to be an element, an object in the category C that this functor is going to pick out. Then we have a whole category of functors from I into C, and natural transformations between those functors. And that category is the product of C with itself, like I times. So rather than being the binary product of C with itself, like the product category, C cross C, it's like the C cross C cross C cross C, like I times. Make sense? Any questions, concerns, or notes so far on this? All right. Product's pretty straightforward. Okay, so then, yeah, he goes on to give this definition that a category is said to have all finite products if it has a terminal object and all binary products, and therewith products of any finite cardinality. So a given category C has all products, he says small products, if every set of objects C in C has a product. Right, so we can pick any set of objects in C, and we can consider the product of all of those objects, right? All right. So the next section is Hom-sets. So this section is a lot about just sort of defining terms that we're going to use later. So then a Hom-set, what is a Hom-set? Well, a Hom-set is a set of arrows between two objects in a category. And it's specified that applies to locally small categories. And the definition of locally small is that it has Hom-sets. That is, for any two objects A and B, there are some arrows between A and B, and those arrows form a set. And that set is given by, the Hom-set of arrows from A to B is just all the arrows in C from A to B. Right, so it's the set of the arrows for those two objects. All right, so there's one such Hom-set in the category for any pair of arrows. And since these are sets, we get functions between them, which is kind of great. All right, and we have this function, which given an element of this Hom-set, from B to C, and an element of this other Hom-set from A to B, we get an element of this Hom-set. And that is just composition on the arrows. So it's a function, literally like a function on sets. And that function takes two arrows in this category and gives their composite, right? So this is not function composition necessarily. It's arrow composition in whatever category this is. But this construction here is a function. Okay. And he writes, to apply this function at a particular type or at a particular object B to the arrow G from B to C, he writes it this way. So it's like this functor Hom B of something. I guess that comes in the next section. But that applied to the function G, right? And that really means G composed with something, right? So, and this is a function, and this function actually gives us a functor. So, if we consider this to be sort of a hole here in this type, then this construction here is a functor. So given an object in C, it gives you a set, right? So it's a functor from C to set. And given an object that will fit in this hole right here, right? So like take the object B in the category C, and that will give you a set in the category of sets, and that set is the set of arrows from A to B in the category C. And this functor is called a representable functor. And it's called the covariant representable functor, and there's a contravariant one as well that works, the other way around, where the hole is in the contravariant position, right? Rather than being in the domain, in the codomain, it's in the domain. He shows that this really is a functor by proving that the requisite homomorphism law holds, and that's on the bottom of page 48. And then he uses this definition of representable functors to show us a very concise definition of products. So he says clearly, a pair of arrows, if you have P1 and P2, one of them goes from P to A and the other one goes from P to B, they clearly form an element of this set, which is the Cartesian product of, the Hom-set from P to A and the Hom-set from P to B. All right, so you have one element of this set and one element of that set, which is clearly then an element of the Cartesian product of those two sets. Then we have a function like this, which given an element in the Hom-set from X to P, that is given an arrow from X to P, we can get a pair of arrows, one from X to A and the other one from X to B, simply by applying the these two arrows, or composing with these two arrows, P1 and P2. Right? You can check that this type checks, but so this is like, it really is a function, right? It's a function on sets. What we're operating on here are arrows in this category C, whatever that might be. And so then he gives us this concise definition of the product. He says, the object P is a product for A and B precisely when the function V is an isomorphism. So given these types, or given this type for V, if V is an isomorphism, then P is the product of A and B, and vice versa. Like it's precisely when. So then what would it mean for V to be an isomorphism? Well, it would mean that for every pair of elements F and G in this, or every element in this type, so in this return type, so for every element in the return type, we can get an element in the argument type, such that if we apply V to that, we get the element we started with, right? So it's V is going to be its own inverse. Or sorry, V is going to have an inverse, right? So there's going to be some unique element X that we could get for each such pair of arrows. And that arrow is going to be from X to P, and it's going to be selected by the inverse of V. So then for any two arrows, F and G, so one from X to A and the other one from X to B, there's going to be this unique arrow from X to P, such that V of U is the pair F and G, right? So we go back to where we started. And since the definition of V is such that V of U is, P1 composed with U and P paired with P2 composed with U, then F is clearly P1 composed with U and G is P2 composed with U, right? That is, V of U is F comma G. And that's exactly the universal mapping property of the product, right? So this and that. So we can try out whether that actually works in Hask, right? So for products in Hask, we have the Cartesian product. So it takes, a function from X to the pair AB, and it should return two functions, one from X to A and one from X to B. Then it just so happens here that the category is the same, right? So Hask and the category that these Hom-sets are in are the same. So that can be a little bit confusing, but so this is a product in the Hask category, and this thing here is actually a product of Hom-sets, right? But it happens to coincide. Right, so this works out in Hask because, we just take this function X and we compose it with P1 and P2 to get our, sorry, not P1, first and second, right? And then the inverse of V is, we have a pair of functions, and that should give us a single function from X to the pair, and that works out, right? Because we have the pair FG and we have X, so we apply F to X and G to X, and that gives us a pair. Great. So then what is this saying? It's actually saying something very similar that we talked about 2 sessions ago. It was that in any category, or in any locally small category, A cross B is a product of A and B if there's an isomorphism between these arrows from X to A cross B and the pair of arrows X to A and X to B, right? So if there is an isomorphism between these two objects, then then this is a product. A cross B is a product. And note that both of these are in set. So this is an isomorphism in set. It's an isomorphism on the Hom-sets. And what he goes on to talk about preserving products. He says that a functor f preserves products if f on the product of A and B is the product of f of A and f of B. All right. That is, if this canonical comparison arrow is an isomorphism, which is, like this V thing that we had. For endofunctors in Hask, if we consider whether endofunctors in Hask preserve products, then we can write this sort of canonical comparison function, which goes from f of the product of A and B to the product of f of A and f of B. Then that's just going to be, we can implement that because it's going to be like f map on the first of x, f map first over x and f map second over x, right? So we're just going to lift first and second over this functor to operate on this pair. And that should give us the pair f of A and f of B. So then an interesting question that comes up is which functors in Haskell actually preserve products? Like, clearly not all of them do, right? Because is this an isomorphism for any functor in Haskell? The answer is no. But then what do we need? What do we need additionally to make sure that we can write this isomorphism? Right? So let's say like int comp. And we want to write f of A and f of B to f of A comma B. Like, we need something more here because we clearly can't just like take an f of A and an f of B and produce an f of the pair. Right? Or do you think you can do it? Anybody?
Applicative.
You need applicative. That's right. So if you have applicative f, then you can do it. So then you have x and y. So that's going to be, well, comma, mapped over x and y, right? Like this. Sweet. So now we have our answer. That an applicative functor is a functor that preserves products. Great. And that's the end of chapter 2, besides the exercises. So then I guess next time we'll cut this session short, and next time we'll go over the exercises at the end of chapter 2. So the assignment there is to pick an exercise and do it, and then present your solution. All right. Anybody got anything else?
I don't think so. Thanks a lot, Runa.
All right. Thank you.
Thank you.
Later.
Thank you.